Mechanical offset. You're exactly 5 meters from a man holding a child in front of him like a shield. The only chance you got is to take the shot. So you put your dot right on his nose and you press the trigger. And the round hits the child. This breaks new shooters' brains every time. Because your rifle did exactly what you set it up to do. You might even think the bullet comes out of your optic, like in a game. But in reality, the barrel sits about 2.5 inches below your sight, so you had to aim a little higher, and it's slightly more on a taller mount. So one line comes out of the optic and the other from the barrel. Where they intersect is where the 0 is. If you look at this graph, the point of impact is slightly different for every yard going forward. On that hostage shot, you should hold at the hairline instead of the nose. This can also get very dangerous if you're shooting behind cover or leaning against something. Seeing over the cover through your optic doesn't mean your barrel clears it. It's the same when lying prone. While we're up close, the only reticle decision that matters here is dot size. A 2 MOA dot is precise, but slower to find if it's not bright enough. A 6 MOA dot is fast and forgiving, which is why it lives on carry and home defense guns for anything up close. But a dot this big, it can block the target if it's too far away and you wouldn't know how much you are holding over. Canted offset hold. When you tilt the gun like almost 90 degrees, your point of impact will be offset horizontally. A 90-degree cant costs you your bullet's drop in 2 different paths. One is going to be angled toward whatever it's angled, and another one straight down. So when you roll the gun, they roll with it, but gravity still pulls the bullet straight down as normal. High angle hold. A sniper is on a tall building, roughly 1,000 meters high, aiming almost 89 degrees down at a bank robbery situation that's happening 60 feet from the building. He uses the same 0 he had previously set up back on the range, and bam, the bullet hits high. Whether you shoot uphill or downhill, an angled shot will always hit high if you use a flat range 0. Because if you tilt the line of sight distance this way, now the shot looks like an ordinary flat 1,000-meter shot. The bullet flies straight across, and it's always longer than the angled modified distance, which explains why the bullet always hits high. But the gravity vector on the bullet only affects the angled modified flat line distance, which is this distance highlighted here. So we want to find the drop data covering this distance. So for this shot, you would aim right here. But if you use a rangefinder slaved to the rifle like this one, it's going to tell you the true distance from here to here. But it's also going to tell you the flat line distance, so you can quickly find these values from your dope chart. If the situation is flipped, the dope data is still the same, but the gravity and air resistance will fight the bullet much harder than shooting down. So everything you know about flat shooting still works. You're just doing some trigs to solve this problem. BDC holds. Now there's a steel target sitting at 400 yards, and your new scope has a ladder of hash marks stacked right under the crosshair, telling you exactly where the bullet will land at each specified distance. If you know your distance, you just put the right marking on the target and send the round, and you don't even have to think. But there is some nuance to this thing, because those yardages were calculated for a specific bullet. For example, like a barrel twist rate, length, even weight and speed can affect it. Anytime you change the ammo, it will significantly be different from what the reticle is calibrated for. So like mounting the same scope on an AR onto a 308, then your fixed BDC will be completely off the further you go out. If the BDC reticle has a 100-yard 0 mark, like on this L-can in the middle, then people typically 0 at 100. Then they test where those bullets land to verify them. The same goes for this ACOG scope you may recognize on most American military's M4 rifle. That reticle is calibrated for one specific load, so the drops are etched into the glass. BDC is the fastest way there is to hit at mid-range without touching a turret. Milliradian holds. Past 500 yards, the BDC won't be much help, and you graduate to something more grown up, like this one called the Mil Dot. So you're set up on a ridge, and you can aim with this without knowing exactly the target distance. But it requires you to know the size of your target and overlay it with the reticle and do some simple math to figure out the distance. So if a 1 by 1 meter size steel gong takes up 2 mil dots, then if you plug it into the formula, it's 500 meters. If you aimed here, and the point of impact lands 2 MOAs low and 1 MOA to the left, then you just correct it by holding 2 MOAs higher and 1 MOA right. This is why most modern reticles have this Christmas tree type design, with enough reference points to help you make hold corrections. This does require you to know the size of your target or know your previous hold, which people call establishing the dope. Basically, it's the points of impact data you have previously recorded so you can reference it quickly. So this is based on the base 10 system, so each line is 1 mil. What that means is that at 200 meters, 1 mil is 20 centimeters, and so on. At 1,000 meters, 1 mil is 1,000 centimeters, aka 1 meter. Think of it as a ruler inside your scope, and there is another version that uses the MOA unit. The concept is similar, but it basically comes down to which unit of measurement you are most comfortable working with. It's easier to verbalize whole numbers using the Milliradian system. For example, something like 0.4 mil to the left is much faster and less mind-twisty to communicate and spatialize in the brain than saying something like numbers and fractions when dealing with inches using the minute of angle unit. Stick to one and master it is what pros are taught to do. Neither is better. But always remember to match your reticle to your turrets. Mil reticle to mil turrets. MOA reticle to MOA turrets. Mix them up, it wouldn't be fun. But as far as how seasoned pros hold over their reticle, you can either dial the turret so the point of aim is always the point of impact, or you can hold. The first camp will say to hold because it's faster, but this only works if you are very familiar with your setup and you move quickly from target to target. The second camp recommends you to dial, because the nice part is that you make the center of the reticle your thing. It's easier for the eye to focus on this middle part of the reticle than counting through lines and referencing something small that you may have gotten lost or forget where you were just looking at. So, no counting lines under recoil, especially if the reticle is busy. Turret quality can also yield some error in them because no two dials are perfect. Sometimes one dial may completely overshoot what you actually need if it's just a very, very small correction to make. For example, if you only need to make less than a 1/100th of a mil adjustment, but your turrets each turn gives you 1/10 of a mil, you might as well just hold. So dial when the distance is known and you have time to make corrections, assuming there is no wind or gust. Hold when the distances keep changing and assuming you don't get easily lost in the reticle. Army's new Smart Scope's main selling point is so that soldiers can rely on the computer on board to range targets, and it will automatically show where to aim. Wind holds. Picture the perfect shot, but the wind just doesn't give a damn about whatever ballistic app you have. Because wind is constantly changing while your bullet is still in the air, that's also why you hold wind instead of dialing it. Even if you dial, by the time you do, the wind may have already changed. Luckily, this math is already etched onto the glass, so if you need to hold 1 mil to the right and 2 mils up, then this part will be the center of the reticle. This is why each sniper has a spotter to help them. The spotter first figures out the wind's speed and direction, then checks the wind hold for that distance and speed from their dope card or ballistic calculator. If the target is farther away, the longer your bullet hangs in the air, and the more time the wind is resisting on the bullet, and all of that is baked into the calculation. The first time you look through one of these, you're going to hate it, and there is some learning curve to it. Moving target hold. If something is moving, the main job is to find the lead hold using the ambush method. So here is your hold, you stay there, and as soon as the target moves across it, you fire. Then, boom, the bullet intersects the target over here. Another way is to track the target, but this will be difficult if your motor skill isn't smooth enough, or you have a stiff tripod that skips like this while you track. So the math can get very granular the further away it is, assuming there is wind and everything else involved. This is where technology comes in handy to figure out how fast the target is moving using something like a kestrel by figuring out how long the target takes to move over a set distance. 2 seconds or 2.3 seconds actually make a huge difference, and the calculator will take that speed and convert it into lead hold for various distances. In a shooting competition, these targets may move at a set pace, but an enemy soldier or a deer may suddenly stop or slow down, so it can get tricky. Some scopes have these moving targets held for you to quickly eyeball, and some fancy scopes have onboard computer that does all the work and shows an aiming dot in real time, so you don't even have to think. But the core skill for all of these is to predict where the bullet's true path will be, and put your hold there instead of on the thing you want to hit. The 20 MOA cheat hold. This slightly slanted optic mount is actually a thing. While this technique is mostly for the sharpshooter trying to hit something 1,000 yards away, and you really have to arch the barrel up to make that shot. And at a certain point, your scope runs out of elevation dial to hold. If you hold higher, then your sight picture is gone. You cannot dial down 20 MOA any further because you only have, for example, 10 MOA left before the erector assembly hits its mechanical limit. So this super niche method adds another 20 MOAs to free up more upward elevation travel, like this. 20 MOA is hard to tell just by looking at it, so for exaggerated illustration purposes, it's kind of like zeroing an M320, where you aim high, but you tilt the optic. It's the same concept here, but with only 20 MOAs. This is mostly for shots past the 1,000 yards, and you can either add 20 MOAs to the scope mount, or have a rifle that is already made to have that canted angle, like this, shown on the screen. But do not stack both because your close range zero will be way off for your normal bullet trajectory. For example, you will be aiming like this, which you either need to offset the cant MOAs in your hold, unless you are taking a 2,000 yard shot and expect the arc to go like this as an example. This won't be realistic for most centerfire rifle projectiles. If you like this type of simple breakdown, please check out these videos too.